Okay, so you might be wondering why um I didn't include my screencast, and that's because I accidentally turned on my webcam when I was recording my screencast, and I'm not sure if I want that to be public or not. So for now, I'll just upload my explanations. And if I record my explanations separately, then like it'll take a shorter amount of time for YouTube to upload. So that's what I'm going to do. And currently I'm 8th, and hopefully that will stay. So okay, so for problem A, the the best thing you should do here is to use intuition. So if you look at the sample case, you can realize that the reason why the first case is yes and the second case is no is because in the first case 3 is divisible by 6, but this is not. So if you look at the polygon over here, each two sides of the original polygon corresponds to one new side of our new polygon. So and each of the sides of our new polygon has to be the same size. It needs to have the same number of sides of the original polygon. So that means that the number of sides of the original polygon must be a multiple of the number of sides of our new polygon. So the code is pretty simple. You just check if A is a multiple of B. For the second one, basically, if you look at this array here, you can realize the reason why it fails is because you have this 1 here and you have this 3 here, and then this 1 and this 3, basically this 1 and this 3, they don't satisfy this condition here. And you can realize that since j is greater than I, the only way that this can be true is if a of j is greater than a of I. So what we can do is we can sort the array in non-increasing order so that a of j will always be less than or equal to a of I, so that this so that the left part will always be greater than the right part. And the code is also pretty simple here. So just sort A using this comparator, the greater comparator, and then you just output it. And yeah, that's it. For C, because you're working with powers of k, the thing you should do first is you should, for each element in A, you should find its representation in base k. And then since we can only increase, so when I is equal to 0, we can only choose some position and increase v by k to the 0th power. And so that means that in all of our elements in the array A here, only one of them can have a units digit in base k, and that units digit can only be 1. And then the same thing happens for the next digit. Only one of these can have a digit of k, and so I should write this out actually. So let's say that our base is 3, so that's our k, and then let's say the first element in our array is 10, and then the second is 3. So only one of them should have the units digit. So if I write this, so I can write this as 101 in base 3. I can write this as 10 in base 3. So only one of these should have a ones digit in base 3, and that's true. And if we had, if this was instead a 4, and then it will look like this, and that means that we will have 2 numbers with a units digit in base 3. Then this and since we can only increase the units digit like once, getting 10 and 4 is impossible. And there's also the case when, okay, so there's also the case when, for example, if this is 11 and the units digit here will be 2. And since we can only increase it by, when I is equal to 0, we can only increase it by 1. So then, and after we increase that, we can only move on to the next, kind of like the tens digit, and then we can only move on to the hundreds digit. And we can never modify the units digit again. So if there's a 2 here, if it's greater than 1 here, then that means it's also impossible. And then we basically just do this check for the units digit, the tens digit, and also the hundreds digit. And yeah, we just check that only one digit occurs out of all the elements in A, and that the digit has a value of 1. So my code over here, so count basically counts the values of the digits, the sum of the values of the digits. And so in here, J represents the position of the digit. So we start from the units digit, which has a position of 0. And this is the algorithm for finding the digits of a number in base k. So while A is still positive, then A mod k will be the jth digit of A. So we should add that digit to our total count. Then here we increase the position of the digit by 1, and we divide A by k. And lastly, we check our sum of the counts of the digits. And as I said before, if it's greater than 1, if any position has a sum greater than 1, then it's impossible because we can only increase each position by 1. And otherwise, if all positions are less than or equal to 1, then we output yes. So for D, the idea is we'll ignore this condition first. So instead we'll change this condition to for each array there are no pair of equal elements. So if we can solve that, if we solve that for n-1 and n-1 elements and values of n, then we can actually modify it to solve it for this problem. So what we'll do is so given an array of length n-1 and it has values from 1 to n, maybe the array looks like this. Okay, so here I have n equals to 5 and m equals to 5. And how do I transform this array into an array which satisfies this condition? Well, I can just choose any element, and then I can duplicate it, and then now I'll have exactly one pair of equal elements. And then the same thing goes for this element. If I duplicate it, then it will fit here. And then we can also duplicate 3. But notice that we cannot duplicate 5, because if we duplicate 5, then this condition will hold. So if we choose 5 as the index i over here, then the array won't be strictly decreasing after this 5. Okay, so that means we have, since this array has n-1 choices, there's n-1 elements, and we can't choose the biggest value. That means we have n-2 choices to choose the pair of equal elements. Okay, now I'll call the answer for this problem C. So right now we have C times n-2. However, we also need to divide by 2 because we overcounted by a factor of 2. So consider this array. So let's say our final array looks like this, and there are actually two arrays of size n-1 with no repeated elements, which can get to this array. The first array is if we start out with this, and then we duplicate the one over here. And the second array is if we start out with the one on the right, and then we duplicate it to the left. And these two arrays both come to the same array. And so that means we overcounted by a factor of 2. So that's why we divide by 2. So now what we need to do is we need to find what C is. And in order to and remember, C is the number of arrays with size n-1 such that each element is an integer from 1 to n, but there is no pair of equal elements, so all elements are distinct, and this condition will also be satisfied. So since all elements are distinct, what we can do is first we can choose which elements we want to use. So there are a total of m elements, and then our array has size n-1, so we'll choose n-1 of those elements. And then out of those elements, we know we have the max. And then each element can either go to the left or to the right. There are two possibilities. So other than the maximum, there are n-2 elements, and each element has two choices. So this is C. So this turns out to be a formula for C. Now we plug in C into this expression here, and that's how we get our final answer. And so here's my code. Here I calculate the modular inverse, and then here I calculate 2 to the power of n-2 here. Here I calculate this binomial coefficient, so this is m factorial. I multiply it by the inverse of n-1 factorial, and then I multiply it by the inverse of m minus n-1 factorial. And then basically our answer variable stores C right now. So then I just multiply by n-2, then I multiply by the inverse of 2, and then that'll be my final answer. Okay, so E is a pretty straightforward DP problem. So our DP set will be dplr equal to the value if we merge L2R, or -1 if it's impossible. And notice that there's only one possible value for this. We can't end up with multiple values. And one way you can think about this is if you consider so if you actually I think if you consider the logarithms, okay, so you create elements like this, so 2 to the a1, 2 to the a2, ... and then you have your elements 2 to the a I and 2 to the a of I plus 1. And then our operation of replacing them with a of I plus 1, what we actually do in this array is we add these together. So you add them together, and since they're equal, this turns out to be 2 times 2 to the a of I, which is just 2 times 2 to the a of I plus 1. And this is in the subscript. So it turns out to be this. So if we consider the array with powers of 2 like this, then what we do when we merge is we add up 2 elements together. So, and based on this, we can, the value of this range will be determined by the sum of the values in this new array in this range. So since there can only be one sum, that means the value is unique. Okay, so now that the value is unique, I'll actually say how the DP transitions work. So basically you initialize the range with a single element to the value given in the array. Then you iterate through all of the ranges in your DP, and then initially you set the value of each range to -1, and then you simply iterate through the midpoint of the 2 ranges. So you try to split the ranges in half. You try to split the ranges into from I to k and from k plus 1 to j. And then you check that these values, that these have the same values when you merge these ranges, and then you also check that the range can be merged. And if these are both true, then from the problem statement we just replace it with the original value plus 1. Okay, so now we calculate this DP. We actually need a DP2 to find the final answer. So DP2 of I is min elements in prefix I. And the transitions are pretty straightforward. So you iterate through all of j smaller than I, and then if you can merge the range from j to I, so if it's possible to merge it, then you just update dp2 of I with the minimum of dp2 of j plus 1, since you just added a new range from j to I. And then the final answer is dp2 of n. Okay, so for f, basically you notice that this looks a lot like a NIM problem. And then you notice the small constraints over here. So you guess that maybe the pattern for the DP repeats maybe it has a very small cycle. So I'll describe my DP here. So DP1 means we can use any type of attack, and we have DP1 of I means we can use any type of attack, and we have there are I defenders left. And then DP2 of I means we have exactly I defenders left, but we are not allowed to use the infantry attack. And DP3 of I means we have I defenders left, but we are not allowed to use the cavalry attack. And then in order to combine this game for all of the different castles, we need to use some game theory. We can use the XOR for NIM games. So if you don't know that, then you should learn about that, since that's important to solving this problem. So we know that the DP can be calculated using the max from how NIM is calculated. So what we do is we calculate the DP for small values, and then we try to find the first time it repeats. So we try to find the cycle. And in order to find the DP value for large values of I, what we'll do is if it's greater than 200, then because it has a cycle, we'll just mod A with the cycle and then try to use our DP array. We can subtract a huge multiple of P and still have the same value. And if it's smaller than 200, then we'll just take whatever is in our DP array. So then for the final answer, so first we calculate the XOR of all of the NIM values of each castle, And then for each castle, we just try all 3 possible attacks. And we see if the XOR becomes 0. So if it becomes 0, then like we add 1 to the answer because it's a possible move. And then finally just output the answer. Yeah, lastly for G, I don't think I had the best solution for G. Like I feel like my G was complicated. Yeah, yeah, he has a much more simpler solution to G than I do. So I won't describe in detail, I'll just briefly describe it. So basically what I do is I calculate from each, using a segment tree, I calculate from each like node. If you go to the next like special node, how many, the minimum number of steps you need. And then I calculate this using a segment tree which stores the historical minimum value. Then as I DFS, as I go deeper, I can update. So as I go deeper, I assume that for the first few steps, I go into inner node, and then for the next step, I'll just use the autocomplete function to go to my special node. And then once I have these values to go from one special node to the next special node, I basically do a DP to find the cost of going from the root to each special node. And yeah, that's basically it. If you actually are interested, then refer to my very you can refer to my very complicated solution. That's basically it. If you have any questions, then please ask in the comment section below so that I can help you, and you can also help me improve my explanations.